There is an animal alive today whose heart alone weighs as much as a small car. Its tongue can weigh more than an elephant. Its arteries are wide enough that a small child could crawl through them. When it exhales, a column of mist can rise high above the ocean's surface. Underwater, its heartbeat can travel through the sea for miles. Its body grows longer than 3 school buses and heavier than 30 elephants combined. Yet this enormous animal survives by eating creatures smaller than a fingernail. Every day, it must consume several tons of tiny shrimp, like animals known as krill. They gather in drifting clouds through the cold waters of the open ocean. The giant simply swims through them with its mouth open. For most animals, growth eventually meets limits. Blood becomes harder to circulate across long distances. Oxygen becomes slower to reach distant tissues. Food becomes harder to gather in the quantities required to sustain a massive body. Movement itself begins to demand more energy than the body can afford. For most of Earth's history, life never crossed those limits. Dinosaurs ruled the land for more than 160 million years. Some grew enormous, but none of them approached the size reached by this animal. The largest creature to ever live did not appear during the age of dinosaurs. It appeared much later, and it is still alive today. Even more unusual, this giant does not hunt massive prey. Instead, it filters enormous mouthfuls of seawater, trapping drifting animals that gather in dense ocean swarms. But biology normally resists this kind of scale. Far from any shoreline, where the horizon forms an uninterrupted circle and the sea seems to stretch without end, a vast shape moves slowly beneath the surface. At first, there is little to notice, only a subtle darkening of the water and the quiet displacement of the ocean around something immense. Then the shape rises gently upward, revealing a creature whose scale almost defies the eye's attempt to measure it. This is the blue whale, known to science as Balanoptera musculus. Among all animals that have ever lived on Earth, none has surpassed its size. Not the towering reptiles that once walked ancient plains, not the massive predators of vanished oceans, not even the largest creatures preserved in the fossil record. The blue whale stands alone in the history of life as the largest animal the planet has ever produced. An adult blue whale can reach lengths approaching 30 meters, nearly 100 feet from the tip of its narrow snout to the end of its tail. Its mass can approach 200 tons, a living body heavier than a long line of elephants standing shoulder to shoulder. Even in the immense open ocean, a place where distances are measured in kilometers and horizons feel endless, the presence of such a creature reshapes the space around it. The body of the blue whale does not appear bulky or heavy despite this enormous weight. Instead, it carries a long, streamlined form that seems designed by the quiet logic of water itself. The torso narrows gradually toward the tail, creating a smooth profile that allows the animal to glide through the ocean with remarkable efficiency. Light glides across its skin in shifting shades of slate blue and pale gray, patterns that ripple like reflections of distant clouds drifting over the sea. Near the rear of this vast body spreads the tail fluke, a pair of wide horizontal blades that move with slow, powerful strokes. Each downward sweep pushes an enormous volume of water behind the whale, sending the animal forward with steady momentum. The motion feels almost effortless, though the forces involved are immense. A single stroke from that tail carries the whale forward with the quiet authority of a creature perfectly adapted to the open ocean. Unlike land animals that must constantly resist the pull of gravity, a blue whale lives suspended within water that supports its weight. The ocean becomes both environment and structure, allowing such extraordinary size to exist without crushing the body beneath its own mass. Muscles, bones, and connective tissues align in long, flowing proportions, suited for endurance rather than speed, for migration rather than sudden bursts of movement. The head itself forms nearly a quarter of the whale's total length. From above, it appears long and gently tapered, marked by subtle ridges that guide water across the animal's surface as it swims. Beneath this immense skull lies a throat capable of expanding dramatically during feeding, yet even when at rest, the proportions of the whale remain elegantly balanced, each part shaped by millions of years of adaptation to life in the sea. When compared with the great dinosaurs that once dominated the land, the scale of the blue whale becomes even more striking. Many of the largest dinosaurs reached impressive lengths, stretching their necks high above ancient forests or roaming broad floodplains, yet even the greatest among them remained smaller than this modern ocean giant. The blue whale quietly surpasses every one of them, its mass and length exceeding what any land animal ever achieved. Seen from a distance, the whale appears almost unreal, a moving continent of muscle and bone traveling slowly through the water. Yet its movement remains calm and deliberate, each motion shaped by the gentle resistance of the ocean around it. The animal seems less like a creature forcing its way through the sea, and more like a natural extension of the ocean itself, a living current sliding through the depths with quiet power. In the vastness of the open ocean, where ships appear small and storms can rise higher than buildings, the blue whale moves with a scale that belongs to the planet rather than to any ordinary form of life. Its presence reveals a simple truth carried in the slow rhythm of its swimming body. Earth, even in the modern age, still holds room for giants. Deep within the immense body of the blue whale, hidden behind layers of muscle and thick ribs that curve like the beams of a vast living vessel, a heart works steadily in the darkness. It is an organ so large that its presence alone seems difficult to imagine inside a single animal. In the quiet interior of this giant swimmer, the heart moves blood through a body longer than many city streets, maintaining life across distances rarely seen within any other creature. The heart of a blue whale weighs around 180 kilograms, roughly 400 pounds. Its mass rivals that of a small motorcycle or a compact golf cart, yet its shape remains unmistakably familiar. Thick, muscular walls surround a series of chambers, each pulse guiding blood through arteries and veins that branch outward like a network of slow rivers spreading across a continent of living tissue. From this central engine, blood travels along vessels of remarkable scale. The largest arteries carry oxygen through the whale's body in broad, powerful currents, feeding muscles that propel the animal across entire oceans. These vessels must stretch and flex with every movement, accommodating the tremendous pressures created by such a large circulation system. The rhythm of the heart becomes the quiet metronome that keeps this enormous physiology in balance. Despite its size, the heart does not beat rapidly. In calm moments near the surface, the pulse of a blue whale moves slowly, each contraction deliberate and strong. The great chambers fill gradually, then release a powerful surge of blood through the body. The pace remains measured, conserving energy while maintaining the steady delivery of oxygen needed by the whale's vast muscles and organs. When the animal begins a deep dive, that rhythm changes in a remarkable way. As the whale descends into darker layers of the ocean, its heartbeat slows dramatically. Scientists studying these animals have recorded pulses dropping to as few as 2 beats per minute during the deepest phases of a dive. Each contraction becomes spaced across long, quiet intervals, the heart working with extraordinary efficiency while the whale travels through the depths. This slowing of the heart forms part of a broader physiological response that allows the whale to manage oxygen with remarkable care. Blood flow becomes carefully distributed throughout the body, prioritizing essential organs while reducing circulation to less critical tissues. Muscles rely on stored oxygen carried in specialized proteins within the blood and muscle cells, allowing the whale to remain submerged for extended periods without rushing back toward the surface. Within the bloodstream, hemoglobin molecules carry oxygen gathered during each breath. In the whale's muscles, another molecule known as myoglobin stores additional reserves, forming a deep internal supply that can be drawn upon slowly during long dives. Together, these adaptations create a system that stretches every breath as far as possible, sustaining the whale through quiet journeys beneath the waves. The heart itself adapts to these demands with remarkable flexibility. During the descent, the slower pulse reduces the overall consumption of oxygen while still maintaining enough circulation to support the brain and vital organs. As the whale rises again toward the surface, the rhythm gradually quickens, returning to a steadier pace that restores the balance of oxygen throughout the body. Researchers have learned about this hidden rhythm through delicate instruments placed carefully upon the whale's skin, devices capable of sensing the faint vibrations produced by each massive heartbeat. Even within the vastness of the ocean, the signals reveal the quiet cadence of life unfolding inside the largest animal ever known. Within that immense chest, the heart continues its patient work, pushing blood through a body built on a scale rarely imagined in nature. Each pulse travels through the whale like a distant echo, carrying oxygen, energy, and warmth across the long pathways of muscle and bone that allow this gentle giant to roam the open seas with calm endurance. The surface of the ocean carries a quiet boundary between two worlds. Above it stretches open air and sunlight, while below lies a vast interior where light fades and pressure slowly increases. The blue whale moves through both realms, yet its life remains tied to the sky above the water. Like all mammals, it breathes air. At intervals that seem calm and unhurried, the whale rises toward the surface. The ascent happens with slow momentum, the immense body gliding upward until the top of the head breaks the water. A pair of blowholes open briefly, and a powerful breath escapes into the cool air. Moist vapor rises in a tall white plume before dissolving into the wind. In that single moment, the whale replaces the air inside its lungs, drawing in a fresh reserve that must sustain the next journey beneath the sea. The lungs of a blue whale hold an extraordinary volume of air. When filled completely, they contain enough oxygen to supply a body weighing nearly 200 tons. Yet the whale does not rely on lung capacity alone. Its entire physiology participates in the quiet task of storing and managing oxygen with careful precision. Inside the bloodstream, hemoglobin molecules carry oxygen from the lungs to the tissues. In blue whales, these molecules exist in unusually high concentrations, allowing the blood to hold far greater amounts of oxygen than that of many other mammals. The blood itself becomes a moving reservoir, transporting vital oxygen through arteries and veins that reach every part of the whale's vast body. Within the muscles, another adaptation deepens this reserve. The fibers contain large quantities of myoglobin, a dark red protein capable of storing oxygen directly inside muscle tissue. Myoglobin binds oxygen molecules and releases them gradually as the muscles work. This slow release allows the whale to continue swimming, even while far from the surface, drawing from internal stores that extend the time between breaths. As the whale begins a dive, several physiological adjustments quietly unfold. The lungs compress under increasing pressure as the animal descends, allowing gases to move safely within the body while preventing damage from deep water forces. Circulation shifts as well, directing oxygen toward the organs that require it most. The brain and heart remain well supplied, while other tissues reduce their demand and rely more heavily on stored reserves. These changes allow the blue whale to remain submerged for long stretches of time. Many dives last between 10 and 20 minutes, though the exact duration varies with activity and depth. During these underwater journeys, the whale moves with measured efficiency, conserving energy through smooth strokes of its tail. Each movement carries the animal forward without unnecessary effort, allowing the oxygen stored in blood and muscle to last as long as possible. The whale's body also reduces its metabolic pace while diving. Muscles relax into a rhythm suited for endurance rather than speed, and the consumption of oxygen slows accordingly. The ocean itself assists this balance, supporting the whale's immense mass and allowing it to glide through the water with minimal resistance. As the stored oxygen gradually diminishes, the whale begins its return toward the surface. The ascent unfolds steadily, guided by instinct and by the quiet signals within the body that measure the remaining supply of air. When the blowholes finally rise above the water again, another breath enters the lungs, replenishing the system and preparing the whale for the next descent. This cycle repeats throughout the whale's life, breath followed by dive, air exchanged for silence beneath the waves. The rhythm connects the vast ocean depths to the thin atmosphere above, a steady partnership between sea and sky that allows the largest animal on Earth to travel through the deep with patient endurance. Along the upper jaw of the blue whale hangs a structure unlike the teeth found in most large animals. Instead of rows of hard enamel designed for biting or tearing, hundreds of long plates form a curtain inside the whale's mouth. These plates, known as baleen, descend from the roof of the jaw in closely spaced lines, each one flexible yet strong. When the whale opens its mouth, this remarkable arrangement becomes the foundation of a feeding system built not for capturing individual prey, but for gathering entire clouds of life from the sea. Each baleen plate grows from a dense base embedded in the whale's gum. The material itself is keratin, the same resilient substance that forms human fingernails and hair. In the whale, however, keratin takes on a different shape. The plates stretch downward like narrow blades, sometimes more than a meter in length. Along their inner edges, they fray into fine bristles, creating a fringe that resembles a thick brush. When hundreds of these plates hang side by side, the bristles form a living sieve capable of filtering enormous volumes of seawater. The blue whale's mouth is built on a scale that matches the animal's extraordinary size. The lower jaw alone can measure several meters across, forming a vast cradle that opens wide during feeding. Beneath it runs a series of pleated grooves that extend along the throat and chest. These folds of skin remain compressed when the whale swims normally, yet they can expand dramatically when the mouth fills with water. In that moment, the body becomes a flexible container, capable of holding a volume comparable to a small swimming pool. Feeding begins with a sudden acceleration through the water. The whale approaches a dense gathering of prey, building momentum with powerful strokes of its tail. As it reaches the swarm, the jaws swing open and the throat pleats stretch outward. Water and prey rush inside together, pouring into the enormous cavity of the mouth. The expanding pleats allow the body to accommodate the incoming flood, transforming the whale into a living scoop moving through the sea. For a brief moment, the whale carries an immense load of seawater within its mouth. The jaws then begin to close, and the tongue rises slowly upward like a massive piston. This movement pushes the trapped water toward the baleen curtain. As the water is forced outward between the plates, the flexible bristles capture the small animals suspended within it. Tiny creatures remain caught against the dense fringe while the seawater escapes back into the ocean. Once the filtering is complete, the whale gathers the concentrated mass of prey with its tongue and swallows. The entire process unfolds with calm precision, repeated again and again as the whale moves through rich feeding grounds. Each lunge gathers another enormous mouthful, allowing the whale to harvest countless small organisms in a single motion. This method of feeding allows the blue whale to rely on prey far smaller than its immense body might suggest. The filtering system does not chase individual animals or rely on sharp teeth. Instead, it transforms the whale's mouth into a vast net, one capable of capturing entire swarms drifting through the ocean. The elegance of this design becomes clearer when watching the whale glide quietly between feeding lunges. The baleen plates remain hidden inside the closed jaws, suspended like silent combs within the darkness of the mouth. Only during feeding does their purpose fully appear, revealing a structure shaped by long evolutionary refinement. Through this unusual architecture of keratin plates, expanding throat grooves, and powerful jaw movements, the blue whale turns the surrounding ocean into a steady source of nourishment. The mouth becomes both vessel and filter, drawing in great volumes of water and gently separating life from the currents that carry it. In the coldest seasons of the ocean's yearly rhythm, tiny movements begin to gather beneath the surface. Countless drifting organisms respond to changing currents, rising nutrients, and long cycles of light that shape life in the sea. Within these shifting waters, vast populations of krill begin to assemble, forming dense living clouds that stretch through the upper layers of the ocean. Krill are small crustaceans, delicate animals only a few centimeters long. Their bodies appear almost transparent in the water, with faint hints of red and amber reflecting the light that filters down from above. Each individual moves with quick flicks of its tiny swimming legs, yet alone it would seem almost insignificant in the immense ocean. The true scale of krill emerges only when they gather. In certain regions of the sea, krill assemble into swarms of astonishing size. Millions of individuals drift together in loose formations that extend across wide stretches of water. These gatherings move with the slow rhythm of ocean currents, sometimes spreading through layers that reach many meters deep. To passing predators, the swarms resemble shifting veils of life suspended within the sea. For the blue whale, these swarms form the foundation of its diet. Despite the enormous size of the whale's body, its food consists primarily of these small crustaceans. Each krill contains a concentrated store of energy, built from the microscopic algae and plankton it consumes during its own quiet existence. When gathered in vast numbers, krill become one of the most energy-rich resources in the marine world. The ocean provides these swarms most abundantly in colder regions near the poles. During the long days of polar summer, sunlight remains above the horizon for extended periods, nourishing enormous blooms of phytoplankton. These microscopic plants float near the surface, turning sunlight and dissolved nutrients into living matter. Krill feed on this abundance, multiplying rapidly and forming the dense populations that attract larger animals from across the sea. Blue whales follow this seasonal richness with remarkable consistency. As the polar oceans awaken with summer light, the whales arrive in feeding grounds where krill gather in great numbers. Here, the water holds immense concentrations of these tiny crustaceans, creating conditions that can sustain animals of extraordinary size. Within these productive waters, the blue whale spends long periods feeding each day. Its immense body requires tremendous amounts of energy, and krill provide that energy in concentrated form. A single mouthful, gathered from a dense swarm, may contain thousands of individual animals. Through repeated feeding, the whale gradually accumulates the nourishment needed to sustain its massive physiology. Krill themselves contain rich stores of fats and proteins, built through their constant grazing on phytoplankton. These nutrients pass upward through the food web, forming a bridge between microscopic plant life and the largest animal ever to exist. The relationship between krill and whale reflects a delicate balance within ocean ecosystems, where the smallest organisms quietly support giants moving through the sea. While feeding grounds flourish during the polar summer, the rest of the year brings different patterns of movement. As seasonal changes alter the distribution of krill, the whales travel across wide ocean basins in search of suitable conditions. Yet the memory of those rich northern and southern waters remains central to their yearly journey. Within the cold currents of polar seas, where sunlight lingers and plankton blooms spread through the upper ocean, the smallest crustaceans gather in numbers beyond easy counting. There, among drifting swarms of krill nourished by the quiet productivity of summer waters, the largest animal on Earth finds its most important source of food. Movement begins long before the moment of feeding itself. Beneath the surface, the blue whale adjusts its posture with quiet precision, aligning the immense length of its body with the direction of travel. The tail moves in steady strokes, each sweep sending powerful currents through the surrounding water. Gradually, the whale gathers speed, its momentum building through smooth acceleration that carries the animal forward with surprising agility for something of such enormous scale. Ahead, dense gatherings of small marine life drift through the water. Within these shifting layers, the whale senses opportunity, and its motion becomes more purposeful. The streamlined body slices through the sea with increasing velocity, the muscles along its back and flanks coordinating each movement with calm efficiency. Water flows along the animal's sides in broad, silent sheets as the whale approaches its target. At the final moment before contact, the whale opens its mouth. The lower jaw drops downward and outward, creating an enormous opening that approaches a right angle with the upper jaw. For an instant, the animal resembles a vast living gateway moving through the sea. The interior space of the mouth expands rapidly, preparing to receive an incoming surge of water and prey. As the jaws spread wide, the remarkable folds of skin that line the whale's throat begin to stretch. These pleats run from the underside of the jaw along the chest and belly, normally lying flat against the body during ordinary swimming. During feeding, they expand dramatically, unfolding like the flexible walls of an enormous container. The volume of the mouth increases many times over as these pleats extend outward. The whale's forward motion continues during this expansion. Water rushes into the open mouth, carrying countless tiny organisms along with it. The sudden intake forms a powerful surge, filling the expanding throat cavity with a mixture of seawater and drifting prey. The immense body briefly absorbs the force of this inflow, the pleated skin stretching to accommodate the enormous volume. For a moment, the whale carries a vast quantity of water within its mouth. The momentum of the initial lunge slows as the weight of the captured water presses against the jaws and throat. Muscles along the head and neck begin to contract, gradually closing the mouth while maintaining control over the enormous load contained within. As the jaws come together, the whale begins the process of filtration. The tongue presses gently upward, guiding the trapped water toward the structures that line the upper jaw. Along the edges of these structures, countless fine fibers form a dense curtain that allows water to pass while retaining small animals. The pressure created by the whale's movements forces the water outward through this living sieve. Streams of seawater escape back into the ocean, flowing through the narrow spaces between the filtering structures. The prey carried within that water remains behind, collected against the inner surfaces where the fibers form a dense barrier. Gradually, the volume of water within the mouth diminishes, leaving behind a concentrated mass of small organisms. The whale then gathers this remaining prey with slow movements of its tongue, directing the collected food toward the throat. Swallowing follows with calm efficiency, completing a feeding sequence that began only moments earlier with the powerful forward surge of the lunge. This entire process unfolds in a brief yet carefully coordinated series of movements. The acceleration, the dramatic opening of the jaws, the expansion of the throat pleats, and the filtration that follows all form parts of a single biomechanical strategy. Each stage flows naturally into the next, guided by anatomical structures shaped through long evolutionary refinement. After the swallow, the whale resumes its steady swimming rhythm. The throat pleats settle back against the body, and the mouth returns to its streamlined shape. Within the vastness of the ocean, the animal prepares quietly for another pass through the drifting layers of life that sustain it, repeating the powerful feeding behavior that allows such an immense creature to gather nourishment from the smallest inhabitants of the sea. Long before the movement of the whale becomes visible in the open ocean, a quieter balance unfolds inside its body. Every muscle contraction, every slow glide through the water, every powerful feeding lunge carries a cost measured in energy. For an animal of such immense scale, the challenge of maintaining that balance becomes one of the most remarkable calculations in nature. Scientists studying these giants often approach the problem with careful measurements rather than distant speculation. Tiny instruments attached gently to the whale's body record motion, depth, and acceleration as the animal travels through the sea. From these records, researchers can estimate how much energy the whale spends while swimming, diving, and feeding. What emerges from these observations is a picture of extraordinary efficiency hidden within a creature of immense size. At first glance, gigantism might appear to demand impossible amounts of food. A body weighing close to 200 tons seems destined to require endless nourishment simply to remain alive. Yet biological scaling follows patterns that soften this expectation. As animals grow larger, their metabolism does not increase in perfect proportion to body mass. The energy required per unit of tissue gradually declines, allowing larger bodies to operate more economically than smaller ones. Within the blue whale, this principle reveals itself through the slow rhythms of its daily activity. The massive muscles that power its movement consume energy steadily rather than rapidly. The animal travels through the water with long, deliberate strokes that reduce unnecessary effort. Instead of quick bursts of motion, the whale relies on steady momentum that carries it forward with minimal expenditure. The advantages of size extend beyond the movement of muscles. A larger body can store substantial reserves of energy in the form of fat, particularly within the thick layer of blubber that surrounds the whale's body. This stored energy functions as both insulation and fuel. During periods when food becomes scarce, the whale can draw upon these reserves, sustaining itself across vast stretches of ocean where prey may be temporarily absent. Seasonal changes in the ocean reinforce the importance of this energy storage. Productive feeding regions appear in specific parts of the sea during certain times of year. Between these places lie enormous distances of open water. Blue whales travel across these distances with steady persistence, sometimes covering thousands of kilometers, while moving between feeding grounds and other regions of the ocean. The ability to store large energy reserves allows the whale to undertake such journeys without constant feeding. The blubber layer gradually supplies the necessary fuel as the whale swims through quieter waters where prey is sparse. When the whale eventually returns to regions where food becomes abundant, the balance shifts once again toward gathering energy rather than spending it. Gigantism also offers an advantage during feeding itself. Larger animals possess greater momentum when moving through dense concentrations of prey. A blue whale, accelerating into a feeding event, can gather enormous quantities of food in a single motion. The scale of each feeding attempt means that the energy gained from one successful lunge can exceed the energy required to perform it. Researchers observing these patterns have begun to see gigantism not as a biological burden, but as an effective strategy within certain marine environments. When prey occurs in dense patches across vast regions, a large body becomes capable of harvesting those patches with remarkable efficiency. The whale's immense mouth and powerful movement allow it to gather concentrated energy from each encounter. Within the vast cycles of the ocean, this quiet arithmetic continues day after day. Energy flows from tiny organisms into the body of the whale, stored, spent, and replenished as the animal moves across the planet's largest ecosystem. Through careful balance between consumption, storage, and travel, the largest creature on Earth sustains itself within the shifting abundance of the sea. Long before the modern oceans took their present shape, subtle shifts began altering the chemistry and movement of seawater across the planet. These changes unfolded slowly across millions of years, guided by the steady rhythms of climate, shifting continents, and the gradual cooling of Earth's surface. In the quiet mathematics of ocean circulation, a new pattern of abundance slowly emerged. During earlier ages of Earth's history, large regions of the sea remained relatively poor in nutrients. Microscopic plants floating near the surface depended on elements such as nitrogen, iron, and phosphorus to grow, yet these nutrients often remained trapped in deeper waters. Without regular mixing between the surface and the depths, vast portions of the ocean produced only modest amounts of life. Over time, the planet entered a series of powerful climatic cycles now known as the ice ages. Massive sheets of ice expanded across high latitudes, altering global weather patterns and ocean currents. As glaciers advanced and retreated, winds strengthened in many parts of the world's oceans. These winds began to stir the upper layers of seawater more vigorously than before. With stronger winds came a process that would gradually reshape marine ecosystems. Surface waters were pushed aside in certain regions, allowing colder water from the depths to rise upward. This upward movement, known as upwelling, carried with it large quantities of nutrients that had accumulated far below the reach of sunlight. When these nutrients reached the illuminated surface, microscopic algae responded almost immediately. Phytoplankton populations expanded rapidly, spreading through sunlit layers of the sea like drifting gardens suspended in water. The tiny plants converted sunlight and dissolved minerals into organic matter, forming the base of a newly enriched food web. The increase in phytoplankton soon echoed upward through other layers of marine life. Small crustaceans and other planktonic animals multiplied as they fed on the abundant algae. Among them, krill found particularly favorable conditions. Their populations expanded in the cold, nutrient-rich waters where phytoplankton blooms occurred seasonally with remarkable intensity. In these regions, the ocean began to concentrate life into dense biological gatherings. Vast swarms of krill formed within productive waters, shaped by upwelling currents and seasonal sunlight. These swarms sometimes stretched across kilometers of ocean, forming immense reservoirs of energy created by countless tiny organisms. Such dense concentrations of prey altered the possibilities available to larger animals. In earlier oceans, food may have been too scattered to support creatures of truly enormous size. Predators needed to spend large amounts of energy searching for widely dispersed prey, limiting how large their bodies could become before the cost of feeding outweighed the benefits. The newly enriched oceans offered a different landscape of opportunity. When prey gathered in vast clusters, large animals could harvest significant energy in a single feeding event. This shift favored creatures capable of moving efficiently through open water and capturing large volumes of prey at once. Within this changing environment, the evolutionary path toward gigantism became more practical. Large marine animals could travel between productive feeding regions while relying on their size to store energy gathered during periods of abundance. The balance between effort and reward began to favor bodies larger than those seen in earlier ages of the sea. Over time, the ocean's productive zones continued to support increasingly large inhabitants. The intricate chain-linking sunlight, microscopic algae, krill, and enormous marine predators formed a system capable of sustaining animals whose scale would once have seemed impossible. Within these nutrient-rich waters shaped by winds, currents, and cycles of ice, the ocean gradually transformed into an environment where vast concentrations of life appeared seasonally across the globe. In these places, the sea no longer offered only scattered nourishment, but entire drifting fields of food, a living abundance that could sustain the largest animals ever to swim through Earth's oceans. The story of whales does not begin in the open ocean. Long before their bodies stretched into the immense forms that now travel through the sea, their ancestors moved across solid ground. The earliest chapters of this lineage unfold along ancient shorelines where rivers met warm coastal waters in landscapes very different from the vast marine world that whales now inhabit. Roughly 50 million years ago, during a period when Earth's climate was warmer and forests covered much of the land, certain mammals lived near shallow waterways in what is now South Asia. Among these animals was a small creature known to science as Pakicetus. At first glance, it resembled a land-dwelling mammal with slender legs, a long snout, and a body suited for walking across riverbanks and floodplains. Yet within its skull lay clues that connected it to a future far beyond the land. The bones of the inner ear in Pakicetus carried distinctive features found only in whales and their relatives. These structures revealed that the animal already possessed adaptations for hearing vibrations transmitted through water. Though it likely spent much of its time on land, it probably hunted in rivers and coastal shallows, searching for fish and other small prey in environments where water and land overlapped. From such beginnings, the transformation toward a fully aquatic life began slowly. Over millions of years, descendants of these early mammals spent increasing amounts of time in water. Their bodies responded to this new way of life through gradual changes that accumulated generation after generation. Each small alteration improved the ability to swim, dive, and navigate within aquatic environments. Later forms along this evolutionary path developed limbs better suited for paddling through water. The legs remained functional for movement on land, yet their structure began to shift toward greater flexibility in swimming. Fossils from these intermediate species reveal animals that could still walk along shorelines, but had become increasingly comfortable within rivers and shallow seas. As the transition continued, the skeleton itself began to change in more dramatic ways. The spine lengthened and became more flexible, allowing powerful undulating movements that propelled the body forward through water. The hind limbs gradually diminished in importance, shrinking in size as the animal relied more heavily on its developing swimming ability. At the same time, the forelimbs transformed into broad paddles capable of steering and stabilizing the body while moving through the water. The tail grew stronger and more muscular, eventually becoming the primary engine of propulsion. With each generation, the animal's posture shifted away from a land-based stance toward the streamlined form required for efficient swimming. Changes also occurred within the skull and sensory systems. The nostrils slowly migrated toward the top of the head, a movement that would eventually lead to the blowholes seen in modern whales. The ears adapted further to detect sound vibrations traveling through water, improving the ability to perceive the underwater world. Over tens of millions of years, these gradual modifications produced animals increasingly adapted to marine life. The limbs that once carried weight across land evolved into structures designed for movement within water. The body became longer and more streamlined, while the tail developed into the powerful horizontal fluke that now drives the motion of whales across the ocean. Though modern whales appear completely separate from land mammals, their skeletons still preserve quiet traces of this ancient history. Deep within their bodies lie small vestigial bones that once supported hind limbs in distant ancestors. These remnants serve as subtle reminders of a time when the lineage that would one day produce the largest animals on Earth still walked along the edges of rivers and shallow seas. From those early shoreline hunters emerged a lineage that gradually abandoned the land entirely. Through patient evolutionary change, the descendants of walking mammals became masters of the open ocean, their bodies reshaped by millions of years of adaptation to a world defined not by soil and stone, but by the endless movement of water. In ancient coastal regions where rivers emptied into warm, shallow seas, certain mammals began spending longer periods in the water. Their bodies still carried the structure of land animals, yet each generation showed small adjustments that made swimming easier and movement along shorelines less central to survival. These animals existed between two worlds, neither fully terrestrial nor completely marine. Among the most revealing of these transitional creatures was a species known as Ambulocetus. The name means walking whale, a description that captures its unusual nature. Fossils show an animal with a long body, strong limbs, and broad feet capable of supporting weight on land, yet its skeleton also carries features that suggest increasing comfort in water. The limbs appear powerful enough for paddling, while the bones of the spine show flexibility suited to swimming. The body of Ambulocetus likely moved through water with a motion similar to modern aquatic mammals that rely on both limbs and body undulation. The spine could bend in a vertical wave, allowing the animal to push forward with coordinated strokes of its hind legs. When entering rivers or shallow seas, it probably used its limbs to paddle, while the flexible body contributed additional thrust. Over time, descendants of such animals continued adapting to aquatic environments. The need to move efficiently through water gradually reshaped the skeleton. The limbs, once designed for supporting weight on land, became increasingly specialized for swimming. Joints changed in proportion and flexibility, favoring movements that generated thrust against the resistance of water rather than those required for walking across solid ground. The forelimbs slowly evolved into broad flippers. Bones that once formed hands and wrists remained within these structures, though their proportions shifted as connective tissues and muscles adapted to aquatic movement. The flippers provided stability and steering while the animal swam, helping guide its direction through the water. At the same time, the hind limbs began to lose their original function. Early species still possessed legs capable of supporting movement on land, but in later forms these limbs became smaller and less useful for walking. As the animal's body relied more on swimming than stepping, natural selection favored structures that reduced drag and improved hydrodynamic efficiency. Gradually, the hind limbs shrank until they no longer served as primary tools for locomotion. Their bones became reduced remnants within the body, no longer visible outside the skin. In modern whales, these vestigial structures remain buried deep within the body as small skeletal elements that echo their terrestrial ancestry. While the limbs diminished, another form of propulsion was emerging along the spine. The tail grew longer and more muscular, supported by powerful vertebrae capable of producing strong vertical movements. Over generations, this tail became the central engine of movement in water. Eventually, the end of the tail developed into a horizontal fluke composed of dense connective tissue and muscle. This structure allowed whales to propel themselves through the water using powerful up and down strokes. Unlike fish, whose tails move side to side, the whale's tail pushes vertically, driven by the flexible motion of the spine. This form of propulsion proved highly effective in open water. With each stroke, the tail generated powerful thrust, moving the animal forward while the flippers stabilized its path. The streamlined body reduced resistance as it traveled through the sea, allowing efficient movement across large distances. The transformation from four-legged mammal to fully aquatic swimmer unfolded across millions of years. Each generation carried small anatomical adjustments that gradually shifted the balance between land and water. Limbs that once bore weight on solid ground evolved into steering surfaces, while the growing power of the tail reshaped the entire mode of movement. Within the bones of transitional species like Ambulocetus, scientists can trace this long progression step by step. The fossils preserve a moment in evolutionary history when the ancestors of whales were still learning how to move through water, their bodies experimenting with new forms of motion that would eventually lead to the graceful propulsion seen in modern whales gliding through the open ocean. Along the long path of whale evolution, another quiet transformation unfolded deep within the skull and jaws. Early whales carried teeth suited for grasping prey, much like other carnivorous mammals that hunted fish or small marine animals. Their jaws closed around individual targets, capturing food one animal at a time. Yet as millions of years passed and ocean ecosystems continued to change, a different feeding strategy began to emerge. Within ancient seas, some whale lineages encountered environments where prey occurred not as scattered individuals, but as immense drifting concentrations. Tiny organisms gathered in dense layers within the water, forming living clouds shaped by currents, sunlight, and seasonal productivity. In such places, the challenge of feeding shifted from chasing individual prey toward harvesting entire clusters of small animals at once. Among certain whale ancestors, subtle modifications appeared within the mouth. The teeth, once sharp and distinct, began to change in form. Fossil records reveal species whose teeth were smaller, more widely spaced, or less specialized for grasping prey. These early forms still possessed teeth, yet their feeding habits may already have begun shifting toward a new method of gathering food from the water. Scientists studying these fossils have discovered evidence that the transition from teeth to filtering structures did not occur suddenly. Instead, it unfolded gradually across several evolutionary stages. Some ancient whales appear to have combined both features, retaining teeth while also developing soft tissues within the mouth capable of assisting in filtering small prey from seawater. One such fossil group, known as Adiocetus, provides a glimpse into this intermediate phase. The skeleton of this ancient whale still contains teeth within the jaws, yet the arrangement of the palate suggests the presence of blood vessels and soft tissue structures similar to those that support baleen in modern whales. These clues hint that early baleen may have developed alongside teeth before eventually replacing them. As generations passed, natural selection favored individuals better adapted to exploiting dense concentrations of small prey. Filtering large volumes of water became more effective than capturing individual animals with teeth. Gradually, the teeth diminished in importance and eventually disappeared from the lineage that would become the baleen whales. In their place, flexible keratin plates evolved along the upper jaw. These structures formed the filtering system now known as baleen. Unlike teeth made of enamel and dentin, baleen consists of dense fibers that grow continuously from specialized tissues within the gums. Over time, these plates lengthened and arranged themselves in rows capable of straining enormous quantities of water. The whales that developed this feeding method became known as mysticets, or baleen whales. Their skulls adapted to support large filtering apparatuses, and the shape of the jaws expanded to accommodate wide openings during feeding. The transformation reshaped not only the mouth but the entire structure of the head and throat. With baleen replacing teeth, these whales adopted a fundamentally different approach to survival in the ocean. Instead of hunting individual prey, they gathered countless small organisms in each feeding event. This shift allowed them to take advantage of the immense productivity found in certain marine environments, where tiny animals occurred in enormous numbers. Fossil layers spanning millions of years record the gradual emergence of this strategy. Early toothed whales appear first, followed by transitional species displaying mixed features, and finally, the fully developed baleen whales that dominate modern oceans. Each stage preserves another step in the quiet evolutionary transition from grasping predator to filter feeder. Within the lineage that led to today's largest whales, the disappearance of teeth marked more than a simple anatomical change. It represented the emergence of a new relationship with the ocean itself, one in which the vast abundance of microscopic life became the foundation for supporting some of the largest animals ever to inhabit the planet. Across the long history of life on Earth, many animals have grown to impressive proportions. Fossil layers preserve the remains of towering creatures that once dominated ancient landscapes. Some of these animals reached lengths that still challenge modern imagination, stretching their bodies across vast plains and forests that vanished millions of years ago. Yet, even among the most enormous of these land dwellers, none ever matched the mass of the largest whales that swim through the oceans today. During the age of dinosaurs, certain species evolved into giants of remarkable scale. Long-necked herbivores, such as sauropods, carried bodies that extended more than 30 meters from head to tail. Their skeletons supported enormous torsos balanced on column-like legs, allowing them to reach vegetation high above the ground. These animals stand among the largest land creatures known to have lived. Despite their extraordinary length, however, the weight of these dinosaurs remained limited by the physical demands of life on land. Gravity constantly pulled downward on every bone, muscle, and organ within their bodies. To support such immense mass, their limbs needed to remain thick and strong, forming rigid pillars capable of bearing the full weight of the animal above them. This requirement imposed natural limits on how large a terrestrial body could become. Bones could grow only so thick before movement became inefficient. Muscles had to generate enough force to lift and move that weight with each step. Even the joints and tendons experienced enormous stress as they absorbed the impact of walking across solid ground. For animals living on land, every movement carried the burden of supporting their own mass against gravity. Standing still required continuous structural strength, and locomotion demanded considerable energy simply to lift and shift the body forward. As size increased, these challenges grew more severe, gradually placing an upper boundary on the mass that terrestrial animals could sustain. The ocean offers a very different environment. Water possesses a natural buoyancy that counteracts much of gravity's pull. A body immersed in seawater experiences an upward force that supports a large portion of its weight. Instead of resting entirely on limbs or skeletal pillars, the mass of the body becomes partially supported by the surrounding fluid. For large marine animals, this buoyant support changes the balance of physical forces acting upon the body. Bones no longer need to withstand the same crushing loads experienced by land animals. Muscles can focus on propulsion through water rather than supporting weight against gravity. The skeleton becomes free to evolve shapes better suited for swimming and stability rather than standing upright. This difference allows marine animals to explore body sizes that would be impossible on land. As the body grows larger, the surrounding water continues to provide support, preventing structural stress from rising in the same way it would under terrestrial conditions. The ocean effectively becomes a vast medium that distributes weight more evenly across the body. The marine environment also encourages movement patterns that suit large bodies. Instead of lifting limbs with each step, whales glide through water with smooth propulsion generated by the tail. Momentum carries the body forward between strokes, reducing the energy required for continuous movement. Large size becomes less of a burden and more of an advantage in maintaining steady motion through open water. Within this fluid world, the limitations that once restricted the size of terrestrial giants fade away. The ocean's buoyancy, combined with the efficiency of aquatic locomotion, allows marine animals to grow far heavier than any creature supported solely by land. Dinosaurs remain among the largest animals ever to walk across Earth's continents, yet their bodies always existed under the unyielding pull of gravity. In contrast, the oceans provide an environment where mass can expand far beyond those terrestrial boundaries. Within that immense and supportive medium, whales eventually achieved a scale that no land animal, ancient or modern, has ever been able to match. Far beneath the surface, where sunlight fades into a dim blue twilight, another form of movement travels through the ocean. It does not disturb the water with ripples or currents. Instead, it moves invisibly, spreading outward through the deep and long rolling vibrations. These are the voices of blue whales, carried not through air but through the dense body of the sea itself. A blue whale does not sing in the way many smaller whales do, weaving elaborate melodies through the water. Its voice takes a different form, built from slow, powerful pulses that unfold over long stretches of time. Each call emerges as a deep resonance that begins within the whale's chest and passes outward through specialized structures inside the head and throat. The resulting sound moves through the surrounding water as a low, steady tone. Many of these calls exist at frequencies far below the range of human hearing. Some descend to around 10 Hz, vibrating slowly enough that the individual pulses stretch across several seconds. Though nearly silent to human ears, these frequencies travel through seawater with remarkable efficiency. The dense medium of the ocean carries such low tones across vast distances without losing much of their strength. Within the deep layers of the sea, a single blue whale call may travel hundreds of kilometers before fading into the background vibrations of the ocean. In certain conditions, these sounds can move even farther, guided by the natural structure of the water itself. The ocean contains layers where temperature and pressure create pathways that channel sound waves across entire basins. When a blue whale releases one of its low calls, the vibration spreads outward in expanding circles. The sound passes through drifting particles, across rising currents, and through enormous volumes of water that stretch far beyond the horizon. Somewhere in that distant space, another whale may receive the signal, sensing the faint tremor through sensitive hearing structures adapted for underwater sound. These calls serve as a means of communication between individuals separated by great distances. The ocean often appears empty at the surface, yet within its depths, whales may remain connected through these traveling vibrations. A call released in one region can reach another whale far beyond visual range, allowing animals to remain aware of each other across immense stretches of ocean. The structure of the calls themselves often follows repeating patterns. Certain sequences of pulses occur again and again within a population, forming rhythmic phrases that continue for minutes at a time. Over years and decades, these patterns may shift gradually, changing as groups of whales adjust the structure of their calls. Researchers studying these vocalizations place listening instruments deep within the ocean, devices capable of detecting the low frequencies produced by whales. These hydrophones capture the slow pulses moving through the water and transform them into recordings that reveal the presence of whales traveling far beyond the reach of sight. Within these recordings, the calls appear as long descending tones or repeating rhythmic pulses, each one representing the voice of an animal moving quietly through the sea. The sounds often continue for hours, forming a distant chorus that drifts across the underwater landscape. Though the ocean may appear silent to human observers standing on the surface, its depths carry an ongoing conversation among the largest animals ever to live. Through vibrations too low for ordinary hearing, blue whales exchange signals that travel across the immense spaces they inhabit. In this way, the deep ocean becomes a vast acoustic environment where distance does not always prevent connection. The slow voices of these giants move patiently through the water, linking individuals separated by miles of open sea. Their calls traveling steadily through the quiet pathways that exist within the ocean's hidden architecture. Beneath the restless surface of the sea lies a world where sound behaves very differently from the air above. Water is dense and tightly packed, allowing vibrations to travel through it with remarkable strength and clarity. Within this submerged environment, sound becomes one of the most effective ways for animals to perceive their surroundings and communicate across great distances. When a vibration enters seawater, it moves as a series of pressure waves that push and pull the surrounding molecules. Because water is far denser than air, these waves travel faster and lose less energy as they move. A sound produced underwater can continue for long distances before fading, especially when it occupies the lower ranges of frequency. The ocean itself is not uniform in temperature or pressure. Layers form throughout the water column as sunlight warms the surface, while deeper regions remain colder and heavier. Pressure increases steadily with depth as the weight of the overlying water grows. These variations shape how sound waves bend and move through the ocean. In many parts of the sea, the interaction between temperature and pressure creates a remarkable feature known as the deep sound channel. Within this layer, sound waves become trapped between slightly warmer water above and higher pressure below. Instead of dispersing in all directions, the vibrations are guided along this channel, allowing them to travel enormous distances with minimal loss of strength. The deep sound channel often lies several hundred meters beneath the surface, though its exact depth varies depending on local ocean conditions. Within this narrow band, sound waves curve gently upward and downward as they move, repeatedly returning toward the center of the channel rather than escaping into surrounding layers. The result is a natural pathway that carries sound efficiently across entire ocean basins. When large marine animals produce low-frequency calls, those vibrations can enter this channel and begin traveling outward along its length. The water surrounding the sound channel acts almost like invisible walls that guide the sound forward. Each pulse spreads gradually across the ocean, maintaining much of its original energy as it moves through the deep. Because of this phenomenon, a single call released in one region of the sea may travel hundreds of kilometers before weakening beyond recognition. Under favorable conditions, the vibrations can move even farther, crossing vast stretches of open water that would otherwise seem silent and empty. For animals that rely on sound, this acoustic landscape creates opportunities for communication across distances far beyond the reach of sight. The ocean may appear boundless, yet the pathways created by temperature and pressure allow signals to connect individuals separated by immense spaces. Within this underwater environment, low-frequency sounds prove particularly effective. Longer wavelengths interact gently with the water, losing less energy as they move. High-pitched sounds tend to fade quickly, but deep vibrations persist, carried forward by the natural structure of the sea itself. Blue whales produce calls that fall precisely within these favorable frequencies. Their deep tones travel slowly but powerfully through the water, entering layers where the ocean's structure guides the sound across remarkable distances. Through these pathways, the voices of whales can move far beyond the immediate presence of the animal that produced them. Researchers studying the ocean's acoustic environment have learned to listen within these hidden channels. Instruments placed deep beneath the surface record vibrations passing through the water, capturing faint signals from whales moving far beyond the horizon. In this way, the ocean reveals itself not only as a vast body of water, but also as an immense medium for sound. Beneath its shifting surface lies an intricate acoustic network shaped by temperature, pressure, and depth. Through that network, slow traveling vibrations move quietly across the sea, allowing distant voices to pass through the dark water with patient persistence. Across the turning of the seasons, the oceans themselves seem to shift in character. Currents alter their strength, temperatures change gradually across great distances, and the distribution of life moves with these slow transformations. Within this moving environment, blue whales follow a pattern that stretches across entire ocean basins, traveling between regions that offer different conditions at different times of the year. These journeys unfold over thousands of kilometers, linking distant parts of the planet through a quiet rhythm of movement. During certain months, blue whales gather in colder waters, where food becomes especially abundant. In other seasons, they move toward warmer regions of the ocean, places where the conditions are more suitable for reproduction and the early life of calves. The migrations begin gradually rather than all at once. Individual whales depart feeding areas over extended periods, moving steadily through the open sea. Their path is not marked by visible boundaries or obvious landmarks. Instead, the whales travel through vast expanses of water, guided by internal rhythms and environmental signals that remain only partly understood. As they move across these immense distances, the whales maintain a steady pace, suited to endurance. The powerful strokes of the tail propel the body forward with measured consistency, allowing the animal to cover large stretches of ocean without sudden bursts of speed. Day after day, the whale continues along its route, passing through regions where the water may change in temperature, clarity, and current. Some of these migrations rank among the longest regular journeys known in the animal kingdom. A blue whale may travel from polar feeding grounds toward tropical or subtropical waters and later return along a similar path when seasonal conditions shift again. These routes can span entire ocean basins, connecting distant ecological zones through the movement of a single animal. The reasons behind these migrations lie in the changing productivity of the oceans. Certain regions support immense concentrations of prey only during specific seasons. In colder waters near the poles, long periods of daylight during summer allow microscopic plants to flourish in large numbers. These blooms provide the foundation for dense populations of small marine animals that gather in these productive environments. When the season begins to change and daylight decreases, the distribution of this food supply gradually shifts. The whales respond by moving away from areas where feeding becomes less reliable. Their journeys carry them toward warmer waters where breeding and calving can occur under conditions more suitable for young animals. Within these warmer regions, the ocean often becomes calmer and less demanding for newborn calves. The young whales begin life alongside their mothers, growing rapidly during the early months after birth. During this time, the adult whales continue to travel, preparing for the next stage of their long seasonal cycle. The exact routes followed by blue whales vary among populations scattered across the world's oceans. Some travel along the eastern and western edges of large continents, while others cross open stretches of sea between distant regions. Modern research using satellite tracking has begun to reveal portions of these routes, tracing the movements of whales across thousands of kilometers of open water. Even with these advances, much of the journey remains hidden within the vastness of the ocean. The whales move quietly beneath the surface, often beyond the reach of ships or observers. Their migrations continue year after year, linking distant feeding grounds with breeding areas separated by enormous distances. Within the great currents and seasonal cycles of the ocean, blue whales follow paths that span a significant portion of the planet. Through patient movement and steady endurance, they connect regions of the sea that change with time, forming one of the most extensive migration patterns known among living animals. The beginning of a blue whale's life unfolds quietly within warm ocean waters, far from the intense feeding grounds that sustain adults during other parts of the year. In these calmer regions, a mother carries her developing calf for many months before the moment of birth finally arrives. When the calf enters the water, it already possesses a size that would astonish most other marine animals. A newborn blue whale calf can weigh between 2 and 3 tons at birth. Its body may stretch more than 7 meters in length, already larger than many fully grown marine creatures. Despite this remarkable size, the calf remains entirely dependent on its mother during the earliest phase of life. The young whale must quickly learn to swim beside her while adapting to the vast environment that now surrounds it. Almost immediately after birth, nourishment becomes the central focus of the calf's development. Like all mammals, blue whales produce milk to feed their young. The mother carries specialized mammary glands positioned along the underside of her body, allowing the calf to receive milk while swimming alongside her. When feeding begins, the calf presses against the gland, and the mother releases milk into its mouth through muscular contractions. The milk itself is extraordinarily rich in energy. Unlike the milk produced by most land mammals, whale milk contains a very high concentration of fats and nutrients. This dense composition allows the calf to obtain large amounts of energy from each feeding, supporting the rapid growth required for survival in the open ocean. Over the course of a single day, a blue whale calf may consume up to 200 liters of milk. This enormous intake fuels a rate of growth that ranks among the fastest known in the animal kingdom. The calf's body expands rapidly, adding weight and strength with each passing day as it swims beside its mother through the sea. During these early months, the mother maintains a close presence near her young. The calf follows her movements closely, learning the rhythms of swimming and surfacing for air. With each breath and each stroke of its growing tail, the young whale gradually builds the endurance needed for life in the ocean. The energy required to produce such large quantities of milk places significant demands on the mother. Much of the nourishment she gathered earlier during productive feeding seasons now becomes the source of energy that supports her calf's growth. The rich stores of fat within her body are gradually converted into milk, transferring accumulated energy from mother to offspring. As the calf continues to feed, its size increases at a remarkable pace. Each week brings visible change as the young whale grows longer and heavier. The muscles strengthen, the body becomes more streamlined, and the calf gains the ability to keep pace with its mother during longer movements through the water. The early bond between mother and calf remains strong during this period of rapid development. The calf relies on her not only for nourishment, but also for guidance within the vast ocean environment. Swimming beside her offers protection and familiarity as the young whale gradually learns the patterns of movement and behavior necessary for survival. Months pass as the calf continues to grow under this constant care. The steady intake of rich milk transforms the small newborn into a much larger juvenile, preparing it for the next stage of life when it will begin feeding independently on the small marine animals that sustain adult whales. Within the quiet partnership between mother and calf, the largest babies on Earth take their first steps into the immense ocean world. Through nourishment, guidance, and patient growth, a newborn whale begins the long journey toward becoming one of the great giants that move through the seas. Far from the cold, productive waters where adult whales gather their food, there exist regions of the ocean that feel calmer and warmer. These quieter seas serve a different purpose in the life cycle of blue whales. Here, far from the intense feeding grounds of higher latitudes, mothers bring their young into the world and guide them through the earliest stages of life. These nursery regions often lie in subtropical or tropical waters where temperatures remain relatively stable throughout the year. The warmth of these environments offers an important advantage for newborn calves. Young whales enter the ocean with bodies that are still developing the thick, insulating layers of fat that protect adults from colder waters. In warmer seas, the young can conserve energy while their bodies gradually grow stronger. The calm conditions of these regions also reduce some of the challenges faced by newborn whales. Currents may still move through the water, and the ocean always remains vast and dynamic. Yet the environment tends to be less demanding than the colder feeding areas where food concentrations are highest. For a young whale still learning to navigate the sea, these quieter waters provide an important beginning. Within these nursery areas, the bond between mother and calf shapes nearly every moment of early life. The calf swims close beside its mother, following her steady movements through the water. Each rise to the surface for air becomes part of a rhythm learned through observation and repetition. Over time, the young whale gains confidence in its movements as its muscles strengthen and coordination improves. Maternal care during this period extends far beyond nourishment alone. The mother's presence provides guidance in navigating the immense scale of the ocean. By remaining near her side, the calf learns the patterns of movement required for survival. The pace of travel, the timing of breaths, and the quiet awareness of surrounding waters all become part of the calf's growing experience. While the mother continues to feed her young with rich milk, she also adjusts her own behavior to accommodate the needs of the calf. Her movements remain measured, allowing the smaller whale to keep pace without exhaustion. The steady rhythm of swimming becomes both instruction and protection, a pattern repeated day after day as the young whale develops. The warmth of the nursery waters supports this delicate stage of growth. Without the stress of colder environments, the calf can devote more of its energy toward building muscle and expanding its body size. The insulating layer of fat beneath the skin thickens gradually, preparing the young whale for the colder oceans it will eventually encounter. As weeks pass, the calf becomes noticeably larger and stronger. Its swimming grows more confident, and it begins to match the steady pace of its mother with increasing ease. The close companionship between the two continues to shape the calf's early experience of the ocean. These nursery grounds do not remain permanent homes. Over time, the calf will leave these warmer waters as part of the broader seasonal movements that guide the lives of blue whales. Yet during the earliest months of life, these calm regions provide a setting where growth and learning can unfold under the careful presence of the mother. Within these quiet expanses of warm ocean, the next generation of the largest animals on Earth begins its journey. Guided by maternal care and sheltered by favorable conditions, young whales grow steadily until they are prepared to follow the long migrations that define life across the planet's vast seas. During the early decades of the 20th century, a profound change spread across the oceans. Human technology had begun to reach farther into the sea than ever before, bringing new tools capable of locating and capturing animals that had once moved beyond the reach of earlier hunters. Among the creatures most affected by this shift were the great whales that traveled through the world's oceans in slow and steady migrations. For centuries, people had hunted whales using small vessels and simple equipment. These earlier efforts limited how many animals could be captured in a single season. Large whales often remained beyond the reach of such hunts, protected by the vastness of the ocean and by their own immense size and strength. The arrival of industrial whaling transformed this balance dramatically. New steam-powered ships allowed hunters to pursue whales across great distances. Harpoons equipped with explosive tips replaced earlier hand-thrown weapons, giving crews the ability to capture even the largest animals in the sea. Factory ships soon followed, capable of processing whales directly at sea rather than returning to shore after each hunt. With these technologies, whaling operations expanded across entire ocean regions. Fleets of vessels searched for whales along migration routes and feeding grounds that had once supported thriving populations. Blue whales, whose enormous bodies provided large quantities of oil and other materials, became one of the most heavily targeted species. Throughout the first half of the 20th century, hunting intensified as demand for whale products continued to grow. The oil extracted from whale blubber served many purposes at the time, including use in industrial machinery, lighting, and the production of various manufactured goods. Each captured whale represented a substantial resource, encouraging fleets to pursue them relentlessly across the oceans. As these hunts continued year after year, the effects on blue whale populations became increasingly severe. Whales that once traveled through the seas in significant numbers grew harder to find. Entire regions where they had once been common began to fall quiet as the number of surviving animals declined. Scientists later estimated that the global population of blue whales may have been reduced by as much as 90% during this period of intensive hunting. Tens of thousands of individuals were removed from the oceans within only a few decades. For a species that reproduces slowly and invests years in raising each calf, such losses proved devastating. By the middle of the 20th century, blue whales had approached the edge of extinction. In many areas, sightings became extremely rare. The immense creatures that had once moved through ocean basins with quiet regularity were now scarcely encountered even by experienced whalers searching the seas. The decline of these giants did not occur suddenly, but rather through a gradual reduction that unfolded over decades. Each hunting season removed more individuals from a population already struggling to recover. With fewer adults remaining, fewer calves were born, and the pace of decline accelerated. As awareness of this crisis grew, scientists and conservation advocates began to draw attention to the fragile state of whale populations. Evidence accumulated showing that continued hunting at such levels could eliminate entire species from the oceans. The disappearance of blue whales would have represented not only the loss of a remarkable animal, but also a profound alteration of marine ecosystems. The quiet reduction of these immense creatures marked one of the most dramatic population declines ever recorded among large animals. Within the span of a single human lifetime, the largest animals on Earth had been pushed to the brink of disappearance. The oceans that once supported thriving numbers of blue whales now held only scattered survivors, their presence a faint echo of the abundance that had existed before industrial whaling reshaped the fate of these giants. In the years following the intense period of industrial whaling, the oceans carried a silence that had not existed before. The absence of so many whales was not immediately obvious to those far from the sea, yet researchers and observers who studied marine life began to recognize how dramatically populations had declined. The disappearance of such immense animals revealed a fragile truth about even the largest forms of life on Earth. By the middle of the 20th century, scientists studying whale populations began to document the scale of the losses. Records kept by whaling fleets showed how rapidly the number of captured whales had increased, followed by a steady decline in sightings as the animals became more difficult to find. The pattern suggested that continued hunting would eventually remove entire species from the oceans. This growing awareness led to discussions among governments and scientific organizations concerned about the future of whales. Nations that had once participated heavily in whaling now faced increasing pressure to reconsider the practice. Reports presented at international meetings described the dramatic reduction in whale populations and warned that recovery would take decades if hunting continued unchecked. In response to these concerns, international agreements began to take shape. The International Whaling Commission had already been established to regulate whaling activities, but its early measures proved insufficient to halt the decline. Over time, however, pressure from conservation groups, scientists, and the public began to influence new policies aimed at protecting the remaining whales. Gradually, restrictions on hunting became stronger. Quotas were introduced in an effort to limit the number of whales that could be taken each year. For some species, including blue whales, complete protection was eventually proposed as the only viable path toward survival. These proposals reflected the recognition that populations had fallen too low to withstand further losses. The turning point arrived when international agreements finally prohibited commercial whaling for many of the largest species. Nations participating in the Commission voted to implement broad bans designed to end large-scale hunting. Though some countries continued limited forms of whaling under special provisions, the era of widespread industrial harvest began to fade. For blue whales, these protections came at a critical moment. By the time the hunting bans took effect, only a small fraction of the original population remained. The survivors were scattered across the world's oceans, their numbers far below what had once existed before industrial whaling began. Once hunting pressures declined, the long process of recovery slowly began. Blue whales reproduce at a relatively slow pace, with mothers investing significant time in raising each calf. Because of this life history, population growth could not happen quickly. Each new generation required years to reach maturity before contributing to the next. Despite this slow progress, signs of improvement gradually appeared. Researchers conducting surveys began to observe blue whales in regions where they had once become rare. Acoustic monitoring detected their low-frequency calls, moving once again through parts of the ocean where the species had nearly disappeared. Conservation efforts expanded beyond hunting restrictions alone. Marine scientists worked to understand whale migration patterns and habitat use, allowing governments to consider protective measures in areas where whales were known to travel. Shipping lanes and fishing practices were also studied in order to reduce accidental harm to these animals. The return of blue whales has been cautious and incomplete, yet the progress demonstrates the resilience of life when given the opportunity to recover. Though their numbers remain far below historical levels, the presence of these giants in the oceans today reflects the outcome of international cooperation and growing awareness of the need to protect marine ecosystems. Through protective agreements and continued conservation work, the great whales that once stood at the edge of disappearance have begun a slow return. Their recovery unfolds gradually across decades, carried forward by each new generation that enters the ocean under the watchful care of its mother. In the present oceans, blue whales continue their quiet journeys across immense distances, yet the world through which they travel has changed profoundly. Human activity now extends into nearly every region of the sea, shaping the conditions through which marine life must move and survive. Although large-scale commercial hunting has largely ceased, other challenges have emerged within the modern ocean environment. One of the most immediate dangers comes from the steady movement of ships that cross the world's oceans each day. Global trade depends heavily on maritime transportation, and enormous vessels travel along major shipping routes connecting distant ports. These ships move through many of the same regions that whales use during migration or feeding. Because blue whales often swim close to the surface when breathing or resting between dives, they sometimes occupy the same layers of water through which ships pass. The immense size and speed of modern vessels leave little opportunity for whales to avoid a collision once the two paths intersect. When such encounters occur, the results can be fatal for the whale. Ship strikes have become one of the leading causes of direct human-related mortality for large whales. Researchers studying whale populations have documented injuries and deaths linked to collisions with cargo ships, tankers, and other large vessels. In some regions, efforts have been made to reduce this risk by adjusting shipping routes or reducing vessel speeds in areas known to host whale populations. Another challenge arises not from physical contact, but from the growing presence of sound within the ocean. Human activity generates a wide range of underwater noise produced by ships, industrial operations, and various forms of exploration beneath the sea. Engines, propellers, and mechanical equipment release continuous vibrations into the water, adding layers of sound to the ocean environment. For animals that rely on sound to communicate and navigate, this expanding acoustic background can interfere with their natural behavior. Blue whales use low-frequency calls that travel across vast distances through the sea. When human-generated noise overlaps with these frequencies, it can reduce the distance over which whale calls remain detectable. The ocean that once carried whale voices across enormous expanses now contains many additional sources of sound. Continuous noise from shipping lanes can create areas where communication becomes more difficult. In such environments, whales may need to call more often or adjust their behavior to maintain contact with others. Beyond these direct disturbances, longer-term changes in the ocean environment also influence the lives of blue whales. Climate change is gradually altering temperature patterns, ocean circulation, and the distribution of marine life. These changes ripple through marine ecosystems in complex ways that scientists are still working to understand. One important concern involves the small crustaceans that form the foundation of the blue whale's diet. Krill populations depend on stable ocean conditions, including the presence of cold water and seasonal cycles that support the growth of microscopic algae. Shifts in ocean temperature and ice coverage can influence where and when these food sources appear. In regions where krill populations change or decline, the feeding opportunities available to whales may also shift. Blue whales rely on dense gatherings of these small animals to sustain their immense bodies. If environmental changes alter the distribution of krill, whales may need to adjust their migration routes or feeding patterns in response. Scientists continue to study how these environmental changes influence the long-term future of whale populations. The oceans remain vast and resilient, yet they are also sensitive to shifts in climate and human activity. Despite these challenges, blue whales still travel through the sea today, their immense bodies moving quietly across the planet's largest ecosystem. Their continued presence reflects both the resilience of life in the ocean and the ongoing responsibility to understand and protect the complex environment that sustains them. In the immense circulation of the oceans, even the largest animals participate in processes far smaller than their size might suggest. Blue whales travel through marine ecosystems as powerful swimmers and enormous consumers of prey, yet their presence also influences the quiet chemistry of the sea in ways that unfold gradually over time. Their role extends beyond movement and feeding, reaching into the cycles that sustain life throughout the ocean. When blue whales gather food, they often dive deep beneath the surface, where swarms of small crustaceans drift through darker layers of water. After feeding, the whales return to shallower depths, where they breathe and rest between dives. This repeated movement between deeper and surface waters carries nutrients upward through the ocean in a subtle biological process that scientists sometimes describe as the whale pump. During feeding, whales consume large quantities of prey that contain nutrients originally derived from microscopic algae and other marine organisms. As these nutrients pass through the whale's digestive system, they are later released back into the water through waste products. Unlike many marine animals that release waste near the seafloor, whales tend to release these materials near the surface after rising from deeper dives. The result is a vertical transport of nutrients from deeper waters toward the upper layers of the ocean where sunlight reaches. In these illuminated regions, microscopic plants known as phytoplankton rely on dissolved nutrients in order to grow. When nutrients become available near the surface, phytoplankton populations can expand rapidly. Whale feces plays an important role in this process. Although it may appear insignificant compared to the immense scale of the ocean, this material contains valuable elements such as iron and nitrogen that are essential for phytoplankton growth. When released into the water, the waste forms a cloud of nutrient-rich particles that disperse through the surrounding currents. These nutrients can stimulate the growth of phytoplankton in areas where certain elements may otherwise remain scarce. As these microscopic plants multiply, they form the base of marine food webs that support a wide range of ocean life. Small animals feed on phytoplankton. Larger predators feed on those animals, and the chain continues upward through the ecosystem. Through this indirect process, whales contribute to the productivity of the ocean itself. Their feeding activities move nutrients across different depths, while their waste products return those nutrients to regions where plant life can make use of them. The presence of whales, therefore, helps sustain the very ecosystems that support their own survival. The influence of this cycle extends even further through the global carbon system. Phytoplankton play an important role in regulating carbon dioxide in the atmosphere. As these microscopic plants grow, they absorb carbon dioxide from the surrounding water during photosynthesis. Some of this carbon eventually sinks deeper into the ocean when plankton die or are consumed by other organisms. By supporting phytoplankton growth, whales indirectly influence the amount of carbon that marine ecosystems can absorb and store. The nutrients redistributed through whale activity help maintain productive surface waters where plankton communities can flourish. In this way, the presence of whales becomes connected to broader cycles that influence Earth's climate over long periods of time. The role of blue whales within the ocean ecosystem illustrates how even the largest animals contribute to processes that operate at microscopic scales. Their movements through the water connect deep feeding zones with sunlit surface layers, while their biological cycles help sustain the tiny organisms that form the foundation of marine life. Within the vast complexity of the ocean, the actions of whales ripple outward through multiple layers of the ecosystem. Their presence supports the circulation of nutrients, the growth of microscopic plants, and the intricate balance of life that unfolds across the planet's largest habitat. Far beneath the shifting surface of the ocean, the presence of whales influences ecosystems in ways that extend far beyond the lives of the animals themselves. These giants move slowly through marine environments, yet their existence shapes the structure of life across multiple layers of the ocean. Their influence spreads through feeding, migration, and even the quiet conclusion of their long lives. When blue whales gather food, they consume vast quantities of small marine animals that occupy lower levels of the food web. This interaction forms a link between microscopic plant life, the small crustaceans that feed upon those plants, and the enormous mammals that depend on them for nourishment. Through this connection, whales become participants in the delicate balance that governs marine ecosystems. The feeding activity of whales influences how energy moves through these systems. By consuming large concentrations of prey and redistributing nutrients through their biological processes, whales help regulate the flow of materials that support many other forms of marine life. Their movements connect feeding regions with other parts of the ocean, spreading nutrients and biological activity across wide areas. This role becomes especially significant when whale populations are abundant. Large numbers of whales moving through productive regions can influence the density and distribution of prey populations. At the same time, the nutrients returned to the water through whale activity support the growth of microscopic plants that sustain entire marine food webs. Through these processes, whales contribute to the stability of ocean ecosystems. Their presence helps maintain cycles of productivity that influence organisms ranging from microscopic plankton to large predators that occupy higher positions in the marine food chain. The balance between these different levels of life depends on the continuous movement of energy through the ecosystem, and whales participate in that movement. Even after the life of a whale comes to its natural end, its influence continues in a remarkable way. When a whale dies in the open ocean, the enormous body slowly sinks through the water column toward the seafloor. The descent may take hours or even days, as the massive form moves gradually into the dark depths far below the reach of sunlight. When the body finally settles on the seafloor, it becomes the center of a unique ecological event known as a whale fall. In the deep ocean, where food can be scarce and scattered, the arrival of such a large source of organic material transforms the surrounding environment. Scavenging animals soon gather to feed on the soft tissues, beginning a process that may continue for months. As the remains gradually break down, different communities of organisms arrive to take advantage of the nutrients contained within the bones and surrounding sediments. Specialized species that rarely appear elsewhere in the ocean may thrive around these sites, supported by the energy released from the decomposing whale. Some of these deep-sea organisms depend almost entirely on whale falls for survival. Bacteria and other microorganisms break down complex organic compounds within the bones, releasing chemicals that sustain unusual forms of life. Worms, crustaceans, and other animals inhabit the remains, forming temporary ecosystems that can persist for years. Through this process, the life of a whale continues to support marine organisms long after the animal itself has died. The nutrients stored within its massive body are gradually returned to the deep ocean environment, feeding communities that might otherwise struggle to survive in the darkness of the seafloor. Across the immense scale of the oceans, whales influence marine ecosystems through both life and death. Their presence shapes the movement of nutrients, the structure of food webs, and the survival of organisms inhabiting even the deepest parts of the sea. In this way, the giants of the ocean help sustain a network of life that extends from the sunlit surface to the silent depths below. Far out in the open ocean, the life of a whale eventually reaches a quiet and natural end. There are no witnesses in most cases, no dramatic signs visible from the surface. The vast body simply drifts in the water for a time, suspended between currents and gravity, before beginning a slow descent toward the dark seafloor far below. This downward journey marks the beginning of one of the ocean's most unusual ecological events. As the enormous body sinks through the water column, it carries within it a tremendous reserve of stored energy. Muscles, fat, and bone contain nutrients accumulated over decades of life in the sea. When this mass finally reaches the depths, those nutrients become available to creatures that rarely encounter such abundance. The descent itself may take many hours. Water pressure increases steadily as the whale moves deeper, and the surrounding light fades until the body passes into complete darkness. Far below the sunlit surface, the seafloor remains a quiet and sparse landscape where food usually arrives only in tiny fragments drifting down from above. When a whale reaches this environment, it becomes a sudden and enormous source of nourishment. The event is known as a whale fall, a rare occurrence that transforms the surrounding seabed. Within hours, scavenging animals begin to gather around the carcass. Deep-sea sharks, hagfish, and other opportunistic feeders detect the presence of organic material and move toward the site. These first arrivals remove large portions of soft tissue. Their feeding activity can continue for months as the carcass gradually changes shape and structure. The surrounding sediment becomes enriched with organic particles, attracting smaller scavengers that contribute to the process of breaking down the remains. As time passes, a second stage begins to emerge. Microorganisms colonize the bones and surrounding materials, initiating chemical reactions that release compounds capable of sustaining life in the deep ocean. Bacteria play a central role in this transformation, converting organic substances into forms that support specialized communities of organisms. Among the most remarkable inhabitants of whale falls are bone-eating worms belonging to the genus Osedax. These unusual animals lack mouths and digestive systems in the conventional sense. Instead, they extend root-like structures into the bones themselves, allowing symbiotic bacteria within their bodies to break down complex compounds and extract nutrients. Around these worms and microbial communities, additional animals begin to settle. Crustaceans, mollusks, and other invertebrates gather around the bones, forming dense populations that may persist for years. the whale fall becomes a temporary oasis within the otherwise sparse deep sea landscape. Over time, the remaining skeleton slowly releases nutrients into the surrounding environment. Chemical processes occurring within the bones continue to support life long after the soft tissues have disappeared. Some whale fall communities have been observed to remain active for more than a decade, sustained by the gradual breakdown of the whale's internal structure. The scale of this transformation reflects the enormous size of the original animal. A single whale fall may sustain dozens of species and thousands of individual organisms. Many of these species appear rarely outside such environments, suggesting that whale falls serve as stepping stones across the deep ocean floor, allowing specialized life forms to spread from one site to another over long distances. In this way, the death of a whale becomes part of the larger cycle of life within the ocean. Nutrients gathered over many years are returned to the depths, feeding organisms that inhabit regions far removed from the sunlit waters where the whale once traveled. Through this quiet process, the influence of a whale extends beyond its lifetime. Even in death, the largest animals on Earth continue to support life in places where resources are scarce and survival depends on rare moments of abundance. In the deep ocean, where sunlight never reaches and food arrives only in drifting fragments, the remains of a whale introduce an extraordinary opportunity for life. The massive skeleton that settles onto the seafloor becomes more than a relic of a vanished giant. Over time, it transforms into a living structure, one that supports a community of organisms uniquely adapted to survive in darkness and scarcity. At first glance, the bones appear silent and still, pale shapes resting on the sediment after scavengers have removed the remaining flesh. Yet within this quiet framework, a different stage of ecological activity begins to unfold. The skeleton contains large amounts of organic material locked inside its dense structure. Lipids stored within the bone tissue hold energy that microorganisms can slowly release. Among the most remarkable inhabitants of these skeletal remains are the bone-eating worms known as osedacs. These delicate animals resemble small red plumes rising gently from the surface of the bones. Their appearance suggests fragile simplicity, yet their biology reveals an extraordinary strategy for survival in one of the most remote environments on Earth. Osedax worms possess no mouth and no conventional digestive tract. Instead, they extend branching structures into the whale bones themselves. These root-like tissues penetrate the hard matrix and absorb organic compounds hidden inside. Within the worm's body live colonies of symbiotic bacteria that perform the chemical work of breaking down these materials. Through this partnership, the worms gain access to a source of energy that few other organisms can use. Over time, clusters of these worms spread across the skeleton, creating small forests of red filaments that sway gently in the deep ocean currents. Each individual worm anchors itself within the bone, drawing nourishment from the ancient tissues that once supported the life of the whale. Their presence marks a stage in the gradual transformation of the whale fall ecosystem. Around the worms, other creatures begin to settle as well. Small crustaceans crawl through the crevices between bones. Mollusks attach themselves to the surface, feeding on microorganisms that grow in the enriched sediments. Bacteria continue to break down complex organic compounds, releasing chemical substances that sustain additional forms of life. Some of these organisms rely on chemical energy rather than sunlight. As bacteria process the materials within the bones, they release hydrogen sulfide and other compounds that support communities similar to those found near hydrothermal vents. Specialized animals adapted to these conditions gather around the whale fall, creating a dense population where previously the seafloor may have supported only sparse life. The whale skeleton gradually becomes a focal point of biological activity in the deep sea. Energy that once fueled the movements of a living whale now circulates through an entirely different community of organisms. Each stage of this transformation draws new species to the site, forming layers of ecological succession that unfold over many years. Eventually, the bones themselves begin to weaken as microorganisms continue their slow work. The energy contained within them disperses into the surrounding sediments, nourishing creatures that inhabit the seabed. Even after the skeleton has largely disappeared, traces of the whale's influence remain embedded within the ecosystem. Through this quiet chain of events, the ocean demonstrates its ability to recycle life on a vast scale. The death of a whale does not represent an abrupt ending within the marine environment. Instead, it becomes the beginning of a new cycle, one that transfers energy from the largest animals on Earth to some of the smallest and most unusual organisms dwelling in the depths. In the darkness of the deep ocean, far from the migrations and feeding grounds where whales once traveled, these bone-dwelling communities continue their patient work. Through them, the legacy of the whale persists, woven into the hidden ecosystems that thrive along the silent floor of the sea. Time unfolds differently in the lives of the largest animals on Earth. While many creatures in the ocean grow quickly and live brief lives measured in only a few seasons, the existence of a blue whale follows a far slower rhythm. From birth to maturity, and through the long decades that follow, their story stretches across nearly a century of ocean history. A blue whale's life begins with rapid early growth, yet the overall pace of its life remains gradual compared with most marine species. These animals can live between 80 and 100 years, sometimes longer. Their immense bodies age slowly, and their biological cycles unfold across decades rather than months or seasons. This extended lifespan reflects the enormous scale of their bodies and the energy required to sustain them. A creature that grows to such extraordinary size must accumulate vast reserves of tissue and fat over many years. The process cannot happen quickly. Each season of feeding adds only a portion of what the whale will ultimately become. The same slow rhythm governs reproduction. Female blue whales typically give birth to a single calf after a pregnancy that lasts close to a year. After the calf is born, the mother invests a long period of time in nursing and guiding the young animal through its earliest stages of life. During these months, the calf grows rapidly while relying entirely on its mother's milk. Once the calf becomes independent, several years may pass before the mother produces another offspring. This long interval between births is a natural consequence of the energy demands involved in raising such a large young animal. A female must rebuild her own energy reserves before another pregnancy can begin. Because of this pattern, blue whale populations grow slowly even under favorable conditions. Unlike smaller animals that reproduce frequently and produce many offspring at once, blue whales depend on the survival of a small number of calves over long periods of time. Each birth represents a significant investment of energy and care. This biological strategy worked effectively for millions of years, while the oceans remained relatively undisturbed by human activity. Large whales thrived in environments where food resources were abundant and natural threats were limited. Over long stretches of time, their populations remained stable, supported by the slow but steady rhythm of reproduction and growth. The situation changed dramatically during the era of industrial whaling in the 20th century. Large numbers of whales were removed from the oceans within only a few decades. Populations that had developed over centuries were reduced at a pace far faster than their natural reproductive cycles could replace. When hunting finally declined and international protections began to take effect, the surviving whales remained scattered across the oceans in much smaller numbers. The slow biology that had once supported stable populations now presented a challenge for recovery. Each generation requires many years to mature and reproduce, extending the time needed for populations to rebuild. Scientists studying blue whale populations today recognize that recovery must be measured across long spans of time. Even with strong protections in place, growth remains gradual because the animals themselves live and reproduce slowly. The birth of each calf contributes to the future of the species, yet the process unfolds at a pace consistent with their long lifespans. This slow rhythm forms part of the deeper story of blue whales. Their immense size, extended lives, and careful patterns of reproduction reflect an evolutionary path shaped by the vast scale of the oceans. Life at such dimensions cannot be hurried. Across the open seas, where migrations stretch across entire basins and generations overlap across decades, the growth of blue whale populations continues in quiet increments. Each new whale entering the world represents a small but meaningful step in a process that unfolds patiently through time, guided by the same deliberate rhythm that has shaped these giants for millions of years. A creature that spends most of its life in the open ocean presents a quiet challenge to those who wish to understand it. Blue whales travel across immense stretches of water, often far from shore and far from the steady presence of human observers. Their size is enormous, yet their world remains largely hidden beneath the surface. For scientists attempting to study these animals, patience and innovation have become essential companions. One of the most valuable tools in modern whale research is satellite tracking. Researchers attach small devices to the skin of a whale using carefully designed tags that remain in place for a limited period of time. These instruments send signals to orbiting satellites, allowing scientists to follow the movements of the animal across the ocean. Through this technology, the paths of whales begin to emerge across digital maps. A single whale may travel thousands of kilometers over the course of a year, moving between distant feeding grounds and warmer regions used for breeding. The routes traced by satellite signals reveal patterns that were once invisible, showing how these giants navigate the vast geography of the ocean. Tracking data also helps scientists understand how whales interact with their environment. By comparing whale movements with information about ocean temperature, currents, and food distribution, researchers gain insight into the conditions that guide these migrations. The data gradually builds a picture of how whales respond to changes in the marine world around them. Another important method of study takes place not in the water, but above it. Advances in drone technology have allowed scientists to observe whales from the air without disturbing them. Small aircraft equipped with cameras hover quietly above the ocean surface, capturing detailed images of whales as they swim and surface to breathe. These aerial photographs provide valuable information about the physical condition of individual animals. By measuring body length and shape from images taken directly above the whale, researchers can estimate overall health and energy reserves. Subtle variations in body thickness may reveal whether a whale has been feeding successfully or struggling to find enough food. Drone observations also offer a unique perspective on behavior. Scientists can document interactions between mothers and calves, feeding movements and social encounters that would be difficult to observe from a boat at sea level. From above, The enormous bodies of whales become visible beneath the water's surface, revealing patterns of motion that would otherwise remain hidden. Sound offers another pathway for understanding the lives of these animals. Blue whales produce low-frequency vocalizations that travel great distances through seawater. Researchers place underwater microphones, known as hydrophones, in strategic locations across the ocean to listen for these sounds. Acoustic monitoring allows scientists to detect the presence of whales even when the animals themselves remain far from view. Each recorded call provides information about where whales are traveling and how often they appear in certain regions. Over time, networks of hydrophones create a map of whale activity across large portions of the ocean. These recordings also help scientists track changes in whale populations. By comparing the frequency of calls across years, researchers can estimate whether whales are becoming more common in certain areas or shifting their migration routes in response to environmental changes. Together, satellite tags, aerial photography, and acoustic monitoring form a quiet partnership between technology and observation. Each method reveals a different aspect of whale life, allowing scientists to piece together the movements and behaviors of animals that spend much of their existence beyond human sight. Through these tools, the story of the blue whale gradually becomes clearer. The largest animals ever to live on Earth leave subtle traces across the oceans, signals carried by satellites, images captured from the sky, and deep resonant calls traveling through the water. By following these signs, researchers continue the careful work of understanding the lives of giants moving through the vast and changing seas. Across the vastness of the ocean, even the largest animals on Earth remain partly hidden from human understanding. Blue whales travel across immense distances, surface briefly for air, and then disappear again beneath the water. Their enormous size suggests visibility and certainty, yet much of their lives continues beyond the reach of observation. Scientists have spent decades studying these animals with increasing precision, yet important mysteries remain. The migrations of blue whales, though mapped in broad patterns, still contain many unanswered details. Satellite tracking reveals general routes between feeding grounds and breeding regions, but the deeper logic behind these journeys is not always clear. Some whales return to familiar locations year after year, following routes that stretch across entire ocean basins. Others appear to change course, exploring regions where few observations exist. Environmental conditions, shifting prey populations, and ocean currents all influence these movements, yet the full complexity of their navigation remains difficult to explain. Within the immense scale of the ocean, a whale may travel thousands of kilometers through waters that contain few human observers. Much of that journey unfolds in silence beneath the surface, where satellites and aircraft cannot easily follow. The precise decisions guiding these migrations often remain invisible, known only through the scattered points where tracking devices briefly reconnect with the orbiting satellites above. Communication among blue whales introduces another layer of uncertainty. Their vocalizations travel extraordinary distances through seawater, carried by the physical properties of the ocean itself. These calls form patterns that researchers can record and analyze, yet the meaning behind many of these sounds remains only partially understood. Some vocal sequences appear to repeat in rhythmic patterns, suggesting structured forms of communication. Individual whales may produce calls that persist across entire populations, spreading through the ocean over time. Researchers continue to examine whether these sounds convey information about location, reproductive readiness, or social interaction. Acoustic monitoring networks detect these deep voices traveling across great stretches of ocean. Hydrophones anchored far below the surface record the low-frequency pulses as they move through the water. The recordings reveal when whales are present in certain regions and how frequently they call, yet the deeper purpose of many vocal exchanges remains uncertain. Beyond migration and communication lies an even more elusive frontier of whale behavior. Much of a blue whale's life occurs far below the surface, where direct observation becomes difficult. Beating dives, long descents into deeper waters, and movements through dark environments take place beyond the reach of most cameras and instruments. Researchers know that blue whales can descend hundreds of meters during feeding activity. At those depths, the environment changes dramatically. Pressure increases, light disappears, and the landscape becomes a vast expanse of cold water. What occurs during the quiet moments between feeding events or during long passages through these deeper regions is still largely unknown. Occasionally, fragments of behavior emerge through new technologies. Tags attached to whales record depth, movement, and orientation as the animal travels through the water column. These instruments provide glimpses of patterns that were once completely hidden, yet even these recordings capture only brief segments of lives that may span nearly a century. The oceans themselves add another layer of complexity. Conditions shift across seasons and decades, altering the distribution of food and the paths whales choose to follow. Changes in ocean temperature, currents, and productivity may influence whale behavior in ways that scientists are only beginning to detect. For researchers, these remaining mysteries form an important part of the continuing study of blue whales. The largest animals on Earth still move through an environment so vast that many details of their existence remain just beyond the edge of human knowledge. Across the open seas, whales continue their migrations, communicate through deep, resonant calls, and descend into waters where observation becomes difficult. Their lives unfold through rhythms that scientists are gradually learning to interpret, revealing a world that remains both familiar and quietly mysterious. Far beyond shipping lanes and distant from the view of most people, blue whales continue their lives within the immense quiet of the open ocean. The surface of the sea may appear empty for days or even weeks, yet somewhere beneath those shifting waves, the largest animals on Earth move slowly through water that stretches across entire continents. For much of their existence, blue whales remain unseen. Their world unfolds across remote regions of the planet where human presence is rare and fleeting. A whale may travel hundreds of kilometers without encountering a vessel, a coastline, or any sign of observation. In these places, the rhythms of ocean life continue quietly, guided by patterns that have existed long before modern technology began to study them. Even when whales pass near human activity, their presence often remains unnoticed. A brief plume of breath may rise above the water and vanish again within seconds. The enormous body that created it slips beneath the surface, leaving only gentle ripples behind. Within moments, the ocean appears unchanged, as though nothing had passed through at all. This ability to move through the sea with such subtlety allows entire populations to travel across vast distances without drawing attention. Groups of whales migrate between feeding grounds and warmer breeding regions, following routes that span thousands of kilometers. Yet these journeys occur largely beyond the awareness of the world above the water. Satellite tracking and research expeditions have revealed fragments of these movements, but the scale of the ocean still allows many migrations to pass quietly through unobserved waters. A whale may spend weeks traveling through deep offshore environments where no ships pass and no observers watch the horizon. During these long passages, the animals remain part of a hidden network of life moving beneath the surface. The quiet presence of blue whales reminds scientists how much of the ocean remains unexplored. Despite their enormous size, these animals inhabit an environment so vast that even the largest creatures can remain largely unseen. A whale measuring more than 20 meters in length can vanish easily within the immense volume of the sea. In many ways, human understanding of blue whales has grown only recently. For centuries, the existence of these animals was known primarily through rare sightings and occasional encounters during whaling expeditions. Only with the development of modern scientific tools did researchers begin to gather detailed information about their migrations, feeding patterns, and communication. Yet even today, knowledge remains incomplete. Large portions of the ocean receive little regular observation, and the daily lives of whales unfold within these distant waters. The brief moments when whales surface to breathe provide only small glimpses into a much larger story taking place below. Acoustic recordings sometimes capture the deep resonant calls of whales traveling through the water. These sounds travel far beyond the range of human vision, carrying across entire ocean basins. A single vocalization may pass beneath hundreds of kilometers of open sea before reaching a listening instrument anchored to the seafloor. Through these recordings, scientists become aware of whales that remain far from sight. The animals themselves continue their journeys through darkness and depth, communicating with others that may be many kilometers away. Their voices reveal a hidden presence, moving steadily through the ocean. This quiet existence reflects the nature of the environment blue whales inhabit. The ocean is immense, layered with currents, temperature gradients, and regions of varying productivity. Within this dynamic world, whales navigate using senses and instincts shaped by millions of years of evolution. As research continues, scientists gradually uncover more of the patterns that guide these giants across the sea. Yet the full story remains larger than any single observation. Across the open oceans of the planet, blue whales continue to travel through deep water that few people ever see, carrying on lives that remain partly hidden within the quiet vastness of the Earth's largest habitat. Long after the surface of the ocean grows calm beneath the night sky, the deep waters of the planet continue to carry the quiet movements of giants. Beneath rolling waves and far beyond the reach of coastal lights, blue whales travel slowly through the largest habitat on Earth, their immense bodies drifting through currents that circle the globe. These animals represent the greatest scale that life has ever achieved. No creature that walked the continents or swam through ancient seas has surpassed their size. Within the living world of today, the blue whale remains the largest animal that has ever existed, a biological achievement shaped by millions of years of evolution in the open ocean. Yet despite this extraordinary scale, their presence is rarely noticed. The ocean is vast enough to hold entire populations without revealing them to the surface world above. A whale may move through hundreds of kilometers of water in quiet solitude, rising briefly for air before disappearing again into the depths. The sea provides the conditions that allow such size to exist. Water supports the immense weight of these animals, freeing them from the limits that gravity imposes on life on land. In this buoyant environment, muscles and bones can expand to dimensions impossible in terrestrial creatures. At the same time, the productivity of marine ecosystems offers the energy required to sustain such bodies. Dense swarms of small animals form the foundation of an oceanic food web that can support enormous predators and filter feeders alike. Through this vast exchange of energy, the ocean becomes a place where life can grow to remarkable proportions. Even so, the existence of blue whales carries a quiet fragility. Their lives unfold slowly across decades, guided by migrations that stretch across entire ocean basins. Each generation emerges gradually, shaped by careful reproduction and long periods of growth. The rhythm of their lives reflects the immense scale of the environment they inhabit. Over time, the oceans have witnessed countless changes. Ice ages have come and gone, currents have shifted, and continents have continued their slow movement across the planet's surface. Through these transformations, whales have remained part of the living fabric of the sea. Today, the oceans still hold these giants. Though human activity has altered many marine environments, blue whales continue to travel across the world's waters, following routes that connect feeding grounds and breeding regions separated by vast distances. Their migrations form part of a quiet continuity that stretches through generations. For those who look across the surface of the ocean, the water may appear empty and still. Yet beneath that surface, immense lives continue to unfold. Whales swim through the darkness of deeper layers, navigate through shifting currents, and communicate through sounds that travel far beyond human hearing. The knowledge that such animals remain part of the living world offers a quiet sense of perspective. The ocean is still large enough to shelter creatures of extraordinary scale, animals whose lives span decades and whose migrations cross entire hemispheres. Within the slow movements of these giants lies a reminder of the vastness of the natural world. Even in an age of satellites and global observation, the oceans retain depths where life continues largely unseen. And somewhere beneath the surface tonight, far from the reach of cities and distant from the noise of land, a blue whale moves through the water with steady patience. The currents carry it forward through dark, open seas, part of a quiet story still unfolding across the planet's largest and most mysterious environment.